This is Cosmographia, the Randall Carlson Podcast.
All right, we are rolling. Welcome back, everyone, to Kosmographia Podcast with Randall Carlson, Brothers of the Serpent, Brad, and Mike. Mike is back.
Mike,
how you doing, buddy?
All right, I'm recovering. Thank you. I was out for a couple of weeks because of illness. Or you could say I was hiking in Patagonia. I don't care.
Mike was
we
hiking.
prefer that you were hiking in Patagonia, and we want you to, go into a little bit of detail here this evening on what you encountered. Yeah, I mean, my understanding was you were down there looking for the Patagonian incarnation of Bigfoot.
Yeah, Patagonian Pete.
Normal guy goes way out there.
Yeah.
Which brings up a question I've wondered. Are there Bigfoot sightings in South America? I've never heard of any.
No.
Not necessarily that I believe in Bigfoot. I don't know what to think about Bigfoot. We'll have to talk about that sometime. But
yeah,
we know there are sightings around. But are there reported sightings in South America of Bigfoot? I don't know.
It's a good question. I've never heard of them.
No, there are cryptid sightings down there, but they're not. I don't think any of Bigfoot. But there
Not
are.
of Bigfoot.
Yeah, it's more chupacabra type stuff down there, isn't it?
Yeah, and there's the skunk ape. But that might be, well,
I think that's Florida.
yeah, that might be Florida.
Skunk ape.
Yeah.
Yeah, I think once upon a time, the skunk ape might have been one of my employees.
But it's like South America has that jungle. It's like everything's a cryptid in there. They're constantly finding new species anyway. No one would be surprised if they found a Bigfoot in there, right?
If they found
A skinless one, though, or a hairless one, I mean.
Hairless Bigfoot, yeah. Man, I don't want to think about that.
Oh, the hairless version of Sasquatch. Right. Yeah, I think I've known somebody like that too.
Like tiny, all shriveled up.
Oh, yeah. Yeah. Mini squanch.
Yeah.
So we've been talking about the younger Dryas events.
Yep.
That's what we were talking about. I remember now. It's all coming back to me. So, yeah, interesting times. And I would think that getting more knowledge out there, more people looking at this period of time is going to be valuable. We need a lot of perspectives on this because it's still not explained yet. There's too many unexplained variables. Bolide impact seems almost certain, but were there other factors? Could there have been a solar factor? I think that's very plausible, and we should certainly explore that as a possibility, because I don't rule out Robert Schoch's ideas. I don't necessarily think it's an either or, actually. I think it's perhaps we're looking at a series of episodes stretching over that 14.6 to 11.6 thousand years ago, centered around 12.9, but it could have been a multiplicity, a very complex series of events that peaked at 12,009, because 12,009 is when we find the impact proxies. But at 14.6, this is the dating for Meltwater Pulse 1A. Now, if that dating is correct, if it's correct, then that means that there was something that happened that injected enough energy into the system to melt copious amounts of glacier ice sheet, that's then returned into the ocean basins and causes this first big pulse of sea level rise. What caused that? Was that impact an earlier impact? Were the traces of such impact have been lost or just haven't been found? Or was it something solar or something we haven't even begun to imagine yet? But the point is that at 14.6, at 12.9, and 11.6, we seem to have highly energetic events. At 12.9, we have impact proxies. To my knowledge, we do not have impact proxies at 11.6 or 14.6. So, but something nevertheless had to have happened, because you don't just suddenly melt, a few 100,000 cubic miles of ice over a very short period of time without some source of energy that's going to trigger that melting. And that is the question: what was the source of that energy? However, at 12.9, we do have this growing body of evidence that suggests the ET component in the form of the proxies we've been talking about, the nanodiamonds, the magnetic grains, the microspherals, the platinum and iridium deposits that are being found in ice, the soot, the carbonized layers that suggest extraordinary biomass burning. So how do you explain biomass burning? Well, could it be the sun? I don't know. I don't know if this, again, there's so much new information coming out every year on so much of this stuff, particularly like solar physics and the role of the sun. It's hard to keep up with it all. But there certainly is growing evidence that the sun is a highly variable star, a lot more variable than anybody had assumed, back 25 or 30 or 40 years ago. In fact, most of the 20th century was the solar constant. But the question is that can small variations in radiative output of the sun be somehow amplified through some kind of positive feedbacks? And that's one of the major questions under discussion right now. But we certainly do know that there's debris out there. We know there's comets. We know there's asteroids. We know that we've had close encounters repeatedly. We've had close encounters just within the last few years, right? So this is nothing too exotic to invoke the idea that there are actual impacts into the Earth on a fairly regular basis. Now, one would assume from the scale and magnitude of these, what we've seen recently is that these objects are not going to be enough to that we've seen recently would not be enough to cause a global catastrophe. Global catastrophe, we're probably looking at least a half a mile in diameter, probably more like a mile above. A mile would be disastrous, perhaps on a continental scale. Would it be disastrous on a planetary scale? Well, it may not be disastrous to where it would essentially wipe out biological life like you would have in the epicenter of a, basically wherever, if you had a kilometer or a mile sized asteroid or piece of a comet nucleus striking the ground, right? Say it's a mile in diameter. Well, that's going to pretty much sterilize everything, probably for somewhere around a radius of 500 miles. And then beyond that, the magnitude of the destruction would begin to fall off. If you're on the opposite side of the Earth, you could probably survive. Unless, of course, you had a seismic wave that traveled around the planet and then converged at the antipode of the impact. Now, that's a possibility that has actually been proposed relative to the Cretaceous Tertiary impact, because the impact site in the Yucatan would have been directly opposite the point that looks very close to the outflow of the Deccan Traps in India. The Deccan Traps was one of course, the great volcanic events in the history of the Earth that is oftentimes blamed for the extinction of the dinosaurs. And that's been one of the ongoing controversies between regarding to the KT extinctions, which, by the way, is not KT anymore. Now it's KP, the Cretaceous Paleogene. And I'm having a tough time with that, because for 30 years I think KT. Now all of a sudden they want me to change to KP, the Cretaceous Paleo. See, it's difficult enough because Cretaceous starts with a C, but we're using the letter K, right? Well, that's because we're already using the letter C for the Cambrian. So we couldn't use the letter C again, or otherwise it would be very confusing. So they used the letter K, which probably in Latin, creta, which means chalk, probably started with a K, is what I'm going to guess. But in any case, the KT boundary is now the KP boundary. So anybody who is actually trying to do research, don't get confused. It's the same boundary. The KT is the KP. It's where the dinosaurs went extinct, and where it's almost 100% verified now that there was a huge impact that left a giant buried crater flanking the Yucatan Peninsula, roughly 66 million years ago. But on the other side of the Earth, you had the Deccan Traps. And the Deccan Traps were just belching out billions of metric tons of sulfate aerosols into the Earth's atmosphere, which would have all kinds of drastic consequences. So my take on it is that, again, it's not an either or thing. I mean, and I don't know, and nobody knows for sure because of the dating resolution is not fine enough to determine, was the Deccan Traps volcanism, that episode, a consequence of the impact? It has been proposed that the shock wave of that impact might be enough to induce these massive plume volcanisms that we see. Because when we go back to the Permian Triassic of 241 million years ago, what do we find there? We find that there was the huge volcanic outflow that left the Siberian Traps, which is, again, one of the gigantic magmatic events in the history of the Earth. And of course, that correlates with the greatest mass extinction on Earth, where 90 to 95% of all species in the oceans went extinct, and something like 80% of all land species bit the dust. That was, it has been said, that was the closest that life came to being wiped out completely on the Earth, was that Permian Triassic. But then we find the Triassic-Jurassic mass extinction, which is one of the Great Five, being associated with the Central Atlantic magmatic plume, which was also a huge outflow. So, but also in each of those Big Five, there's evidence not as definitive and as conclusive as the evidence you find at the KT boundary, but there is evidence at every single boundary for impacts. So it seems to me that there may be a situation where you have impacts. So you have something from outside the Earth associated with massive volcanism inside the Earth, exogenic, endogenic, coupling together, and it's through the combined effects of the exogenic and the endogenic that you get these really, really massively catastrophic disruptions of the biosphere that leads to a very profound loss of species. And the Great Five, of course, that's what characterizes them. Each one of them is that you've got hugely proliferating species, Ordovician, late Ordovician, late Devonian. You got all kinds of fish in the ocean. You've got things going on, and then boom, over half of all species are gone in a very, very short period of time, geologically speaking. So those are the Great Five, and in some of the upcoming episodes, we're going to get into some of those in detail because they're extremely important to understand, especially with the claims that we are now in the midst of an extinction crisis equivalent in severity and magnitude to the Great Five, which is the implication of calling it the sixth great mass extinction. And so that, for that reason alone, but for multiple reasons, it will be worthwhile to look at those events. Then, once having looked at the Great Five, then we come back to the mass extinction at the end of the Pleistocene, 11 or 12,000, 13,000 years ago. And of course, what we see in terms of species loss is that the mass extinction at the end of the Pleistocene doesn't even come close to the Great Five. But in its own way, it was profound and very severe, because basically what happened was the food chain got decapitated almost. And in some of the comments that I've actually been enjoying reading, that's been one of the questions was, regarding species that the modern species. And yes, most of the modern species did exist during the Pleistocene. Yeah. And the question really, I think, more just comes down to the randomness of the event, why some species survived and some didn't. And the fact that some species survived, and we made this point earlier, the fact that some species survived didn't mean that the species didn't come close to extinction. And we cited and talked about the example of the American bison. And here was a species of mega mammal that was reduced to about 300 individuals. I mean, you can't get much closer to extinction than that. And yet, within a little over a century, it's completely rebounded, right? And in retrospect, looking back from 10,000 years hence, you could look back and completely miss the fact that there was this huge bottleneck in the population of American bison. And so we might look back at moose, right? Or any of the North American animals that still exist. Musk oxen, for example, well known to have existed in the Ice Age during the late Pleistocene, but they survived somehow, right? It may have been the luck of the draw. And I don't think anyone can say specifically why one species survived and another one went extinct, other than the fact that, again, it's not a uniform event. It's going to play out differently depending on, latitude, geography, climate, environment. All of these are going to be variables in this equation. Why some species succumb and why some survive, open question at this point. But we do know that these events can certainly eliminate species, and we do see a preference for large species. And when you consider that large species require a greater, more extensive food base, their intergenerational turnover time is much slower than smaller species. Gestation times much longer. So when you have habitat loss, it's going to affect the top of the food chain. You see, because if you have a say a cosmic winter type event, which is basically what we're looking at with the younger Dryas, so you have this sudden cooling that descends over the earth, you're going to have large scale vegetation die off, right? And so if you've got large species that need to eat, hundreds of pounds of vegetation every day, and then the predators that rely on those. So I think you're going to have initially in the event, and if we're talking about an impact event here, and as we get more into the details of this, I think that the model that we're beginning to see is that we're actually talking about a multiple impact event, right? You're going to have, first of all, large-scale species mortality as a result of the impacts themselves. But then you're going to have a whole series of consequences that play out over years, if not centuries, because now you've got this unstable environment. And you're also going to have, in the case of the Balling Alarod younger Dryas shift, you had a shift from relatively benign climate where the glaciers are contracting to a sudden return to full glacial cold. And that was why, the younger Dryas got named after Dryas octopetala, which is the polar wildflower that had already disappeared from northern Europe because of the late glacial warming that was going on. And then it suddenly returns again, showing that you had this sudden return to glacial conditions. So, my point being that, if you've got animals that are depending on the habitat and depending on abundant plant life and vegetation, now suddenly you've got this impact winter, we'll call it, and perhaps this return to full glacial cold, you're going to have a massive vegetation die-off. Now, one of the things we'll be talking about further is the evidence for large-scale biomass burning. So, as we begin to decipher this series of events, it's not simple. It's a very complex series of things that happened. And so we know that at the end of this complex series, about half in North America, about half of the mega mammals didn't survive. About half of them did, right? I think what we were looking at is a threshold type event. And this is now a legitimate conceptual framework for looking at these episodes of change, is that there are thresholds that can get breached, and the breaching of these episodes depends on the amount of energy that's going to be injected into the system, because every change that occurs requires energy inputs of some kind. So what we're coming down to is having to sort this out and look at basically 3,000 years of major global transition that led from the world as it was, say 15,000 years ago, to the world as it is now. And, we've talked about that. And we'll continue to talk about it to really begin to try to clarify these dramatic changes, these planetary scale changes, because in one of the comments, somebody was posting that we'll have to read it. We'll get into it, but I've said repeatedly that the great ice masses of North America, which were basically two distinct ice masses, the Laurentide, which was basically centered over Hudson Bay, reached down to as far almost to northern Ohio, almost to the Ohio River, east of the Mississippi, reached into the Pacific Ocean, actually further than the coastline now exists, because with the lowered sea level, coastline had shifted to the east. The ice sheet followed that. So you had ice sheets that were melting back as the ocean is rising. And so the ice sheets are melting back, revealing those shelves that were buried under the ice. And then the sea is advancing, drowning those shelves. The other interesting thing is that as the ice is removed, it's made this huge depression over the Hudson Bay. And as it's removed, picture this. Here's say the North American craton. Here's the glacier. Weight of the glacier is depressing the center, but around the perimeter, it's rising. That is called the glacial forebulge. So boom, the glacial forebulge. Now you have the deglaciation. So it's relaxing, and then the glacial forebulge goes down. So that complicates trying to determine precisely where sea level was and when it was there, you see. So again, this is not a simple thing here. This is a very complex matter to try to sort all this out, but it sure is fun.
The Laurentide went to the Atlantic, right? It was the other
Laurentide went to the Atlantic, and then in the west, it reached to the almost to the foothills of the Rocky Mountains.
Right. Okay.
And then over Western Canada and Western North America was the Cordilleran ice sheet.
Right.
And it reached from basically northern. It came down where Glacier Park is now is a remnant of the Cordilleran ice sheet, right? And it came down into northern Idaho, the panhandle of Idaho, and northern Washington, and it reached up to Alaska. And for modern comparison, you can kind of think of the Laurentide as being roughly the size of Antarctica, the South Polar ice cap, and the Cordilleran being roughly the size of the ice sheet that's over Greenland. Wow. So you had these two massive ice sheets over North America, which pretty much at their maximum covered the whole northern half of North America under massive amounts of glacial ice. So, that's the kind of thing that as you begin to think about it and contemplate it, you begin to realize, well, good Lord, really have to go through some serious changes to get rid of all of that ice. And, we're not even talking about, you had another Greenland-sized ice sheet that was over northwestern Europe.
Right. That's right.
Yeah.
So
and that's gone too.
So did like our modern little beavers exist back then along with the gigantic ones, or are they?
I think so. Yeah.
So what we're looking at now, that like the little armadillos and little beavers aren't like an adapted version.
The little beaters. Yeah, they were there. Yeah, the little beaters were.
Yeah. Dang beaters.
Those little armadillos.
Yeah.
And the little beaters. Yep. Yeah. I mean, yeah. I don't know specifically about the little armadillos. I think they did. I mean, a lot of I would say probably yes. I mean, if we're looking at the smaller animals, you see, a modern armadillo is not going to be a mega mammal,
right?
And yes, I think that they existed. I mean, in the deposits, well, for example, horses in North America went extinct, but they didn't go extinct in other places in the world.
Right.
And then horses were introduced into North America by the Spaniards.
I think people were asking, some of the comments I saw, people were trying to ask, like, are what some of the animals we see, like, just smaller versions of what was back then, or did they coexist with those giant versions?
I think it was mostly coexists, but I think we did see smaller versions. Now, an interesting case in point would be the American bison, because during the late Pleistocene, you had the super bison, which was huge, right? Now, is North American bison, which is still huge, if you've been up next to one, you know that they're pretty formidable beasts, and you probably wouldn't want one trampling you. But the point is that they're much smaller than the super bison. Now, is it a diminutive version of the super bison? Perhaps. Or is it a completely different species?
Yeah, that's the question.
That's the question.
Right.
I'm
Adapted
thinking
version. Yeah.
I'm thinking that what I've learned, and I could be wrong on this because I am occasionally wrong, but this American bison is a smaller version.
Okay.
Well, we certainly do know, and we talked last week. We mentioned the Pygmy Mammoths, but of course that's because of the insular existence. You know, in other words, they've got limited range, limited habitat range, like the Pygmy Mammoths that are found on the islands, right? So basically, they adapt by getting smaller,
Less food.
Yeah.
less food,
Would
less,
be interesting
less,
to see some,
yeah.
DNA studies on these various.
Yeah, and see, again, that's something that needs to be done, and it is being done, and you know, if I had more time, I would certainly be diving into all of that because it raises very interesting questions about the whole process of evolution and extinction. Because essentially, it appears to me that once we now begin to accept the idea of catastrophic mass extinctions followed by rapid speciation, it does really raise a whole host of interesting new questions about the evolutionary process.
Right. That it happens very quickly and then slows down once all the ecological niches are filled, and then it becomes more stable. But then if another extinction event happens and opens up a whole bunch of places for things to be, then they get filled quickly, and then it becomes more stable afterwards.
Yeah, you have in the aftermath of mass extinction events, you've got this hiatus period where you've got this impoverished fossil record. You know, you look in you look into sedimentary strata and you'll see a lot of fossils, particularly like go back to the Ordovician, a lot of fossils right there up to that boundary. And then it's almost vacant of fossils for a long period of time. And then all of a sudden, boom, there's a lot of fossils again.
Right. Yeah, like the Cambrian explosion, they talk about that.
But,
right?
but those are the actual catastrophic events that give you all those fossils, and then it's followed by not much, right?
By not much, yeah.
So you could make the argument that all of these species existed all the way back. So we had all of the species, and then each catastrophic event wiped out what's in the fossil record.
Yeah.
And then the next one wiped out what's in the fossil record.
Yeah, exactly. And see, here's the thing. Under normal circumstances, creatures that die don't form fossils.
Yeah.
You see, they even modern day elephant mortality. You know, I've got some interesting studies we can pull up here as we're talking about this, and I do intend to pull them up. You know, in the 80s, when these droughts were so severe in sub-Saharan Africa, you had several million elephants that died off, right, during those droughts, and left their remains around water holes that had dried up, right? So you had, and then in addition to that, the 80s saw this rise of poaching, that where they were killing elephants and just taking the tusks and leaving the carcasses on the landscape. Well, we defined the term taphonomy, right? Remember the term taphonomy, which means the processes that lead from the initial death of an individual, the carcass of an individual, and its final preservation as a fossil by whatever route that takes, and whatever the end product of that is, where it's preserved somehow. But what was discovered in the taphonomic studies of elephant mortality in the 80s was that elephants would die. You could come out and there would be, you know, remains of dozens of elephants, and 5 years later, you don't find anything. 5 years. So again, how do you preserve an elephant carcass? Well, you got to bury it. You got to get it away from oxygen. You got to get away from scavengers.
Yep.
So strip away all of the plant matter, all of the topsoil, get down to some bedrock, put the body there, cover it in gravel.
Cover it in sand and gravel.
Mud. Mud needs to be
mud. Yeah, mud.
Anaerobic.
Yes,
mud or clay. Anaerobic environment.
Anaerobic, yes, meaning without oxygen.
And then cover the gravel with mud.
There you go.
Well, for example, that we talked about, the Oralton Farms mastodon was found under a layer of peat that, most likely was wet, soggy stuff that was deposited over the mastodon shortly after his death or immediately after his death and helped to seal it off.
And then there's like all the bog bodies, right? Those mummified human.
Yeah. And that's a good example of anaerobic preservation.
Yeah. Heat bogs.
Yeah.
Heat bogs, yes.
So I was thinking in the scenario where the sulfur dioxide, that was exploding into the atmosphere, and it was raining down at a pH of 1. What was it? I was just thinking about.
Well, yeah, that was the acid rain from.
Yeah.
This is going back to the KT. Yeah.
So that basically created probably an anaerobic environment everywhere.
Yeah,
right?
and in the oceans, anoxia, it's referred to in the oceans when there's this cessation of when oxygen doesn't become available. And then what you have is huge deposits. In fact, they're like off the coast off the mouth of the Nile. They've documented successive layers of sapropylitic muds or sapropels, which basically are, incompletely decomposed organic material that has been flushed into the Mediterranean by huge floods coming down the Nile River. And because they're buried so rapidly, they're cut off from oxygen, so they don't fully decompose. So when they pull up these dredge samples or these core samples, it stinks.
Yeah.
When it's exposed to air. So that would be something interesting to talk about, is these Nile floods. And at some point, if we come back to talk about the Sphinx and the erosion on the Sphinx, we'll tie it in and look at the fact that there have been these extraordinary Nile floods that could have submerged the Sphinx.
A jelly-like ooze or sludge composed of plant remains, most often algae, putrefying in an anaerobic environment on the shallow bottoms of lakes and seas.
Yeah, there you go. What was that? Sapropel?
Yes.
Yeah.
It may be a source material for petroleum and natural gas.
Mm-hmm. Yeah. Read that once more time. That
terms to define since I got this book, so I just had to butt in and do that real quick.
I'm glad you did. In fact, I'm so glad you did. I want you to do it one more time so I can hear it.
Read it.
I just closed the book.
He lost it.
I get it.
Sapropel. It was.
Yeah, that was good.
So basically, my definition was correct. It just wasn't quite as succinct.
Yeah, a jelly-like ooze or sludge composed of plant remains, most often algae, putrefying in an anaerobic environment on the shallow bottoms of lakes and seas.
Great terminology there. Sludge, putrefying. Yeah. Rot. They didn't use the term rotten. I think I might have, but yeah. So that's.
I have pulled up some sapropel from the bottom of a lake before.
Definitely.
Look, you will know if you've pulled up sapropylitic muds. You definitely will know. In fact, I've
next time my buddies were in the lake swimming around and somebody put that
sapropylitic. Yeah. Dispose of that sapropylitic mud.
I don't think they use the word sapropylitic mud.
Wait a minute. They didn't do what, Mike?
I don't think they would have used the term sapropylitic mud. I think it would have been a shorter 4-letter word.
Kyle's buddies, you mean? Oh, okay. I thought you meant the marine geologists that were.
Yeah.
But they did actually use the term sapropylitic mud. But yeah, and you know that if you're out in which I've done many times, been in lakes, my bare feet, and you can feel your foot sinking into that stuff.
Yeah.
Yeah.
Don't bring it up.
All right. So sorry about that digression, folks, but I think it may help you to remember now. So in the future, when we're talking about sapropels, you'll know what we're talking about. Because sapropels are important diagnostic materials. Why? Because when you have a great flood coming off the land, it's filled with organic material. Whether it flows into the ocean or into a lake, what happens is the rapid deposition of that material at the bottom of say offshore. I made reference to the sapropylitic muds off the coast of Egypt, where Nile floods had flushed them out. But you can find examples of sapropels all over the place. And basically, they would be indications of major floods. The thicker the sapropel layer, the greater the flood.
Okay.
So this is the importance of these stinky, putrefying mud deposits. And because of the fact that they're rapidly cut off from oxygen in an anoxic environment, is why they don't decompose. So, yes.
It's fascinating.
So one other thing I wanted to, going back to the extinction events,
Yeah.
it seems to me like the more powerful the catastrophic event that causes the extinction, the farther down the food chain the extinction takes place. Is that generally correct?
I think that, yes, I think generally that's correct.
Right. Because the farther up the food chain you get, the larger and the fewer the animals are in general.
Yes.
So like the extinction always starts at the top of the pyramid there, and the stronger the extinction event, the farther down the pyramid the extinction level goes. In general.
Yeah. In general, yeah. For example, in the aftermath of an extinction level event, you're going to probably have rats surviving a lot more prolifically than mastodons.
Exactly. Yes.
Well, there are going to be more rats.
There's more rats. They can hide in more places, and they need less food and resources. Yeah, exactly.
Yeah, and they reproduce very fast.
Yeah.
And as you go up the food chain, that all of those parameters are changing until you get to the top of the food chain, and now you're looking at, long periods of intergenerational turnover, larger areas of habitable land to provide the food source. So I think that goes a long way towards explaining the terminal Pleistocene extinctions. So anyways, back to to what we've been talking about here in terms of the evidence for an ET event. A great study came out in 2009. The Proceedings of the National Academy of Sciences has actually been pretty fair-minded in their presentation of these controversial ideas. They presented both the pro and the con side in terms of what happened and whether it did in fact involve an ET event. But we were talking about the hexagonal diamonds last week as being one of the diagnostic materials. So this was a study that was published in 2009. Douglas J. Kennett in the same group, basically, who've been doing this work, and they published a paper called Shock-synthesized Hexagonal Diamonds in Younger Dryas Boundary Sediments. And we found that the hexagonal diamonds are called Lonsdaleite, after Kathleen Lonsdale, who was a mineralogist who did some of the very first work on discovering hexagonal diamonds. It says the diamonds occur in a discrete layer that is contemporary with and similar to the organic-rich sedimentary layers described by Haynes across North America. And there we are talking about the black mat layer. And I think the relevance to the discussion we just had is that the black mat layer can almost be thought of as a sapropylitic layer but due to the fact that it tends to be narrower in width, its properties are going to be somewhat different, because you're going to have more. If you have a 3 foot thick or a 6 foot layer of sapropylitic muds, the outer layers are going to have interaction with whatever is above or below, right? And so would a layer 3 inches thick or 2 inches thick, which is very typical for the black mat layer. But so it says the best known geological exposure of this dark sedimentary unit is 1.35 kilometers from the modern coastline on the west side of the canyon. And this is back to this Santa Rosa Island where we left off with, where there's a 44 centimeter thick, organic rich, dark blue, gray, silty, black layer of mud, which rests directly on a gravel deposit at 5 meters depth. The rest of the overlying sequence consists of alluvial sands and gravel. Now, alluvial, again, means flowing water, or it means deposited by water, right? Fluvial means flowing water. Pluvial means rainfall. Pluvial, fluvial, and alluvial.
Got it.
Got it? pluvial, fluvial, and alluvial. Okay,
There's a song in there somewhere.
I think there is. Accelerator mass spectrometry, AMS, carbon-14 dates from upper and lower parts of the sequence are statistically similar, suggesting rapid accumulation of fluvial deposits shortly after 12.9 plus or minus 1,000 years ago. So right there we have this layer of diamonds associated with this black layer that's dating to 12.9. These shock-synthesized diamonds are also associated with proxies indicating major biomass burning. The three proxies are charcoal, carbon spherules, and soot. This biomass burning at the younger Dryas onset is regional in extent and coeval with broader continent-wide biomass burning. Now, coeval means happening at the same time. It also coincides with abrupt sediment mass wasting and ecological disruption, and the last known occurrence of pygmy mammoths on the Channel Islands, correlating with broader animal extinctions throughout North America. The presence of shock-synthesized hexagonal and other nanometer-sized diamonds in younger Dryas boundary sediments in association with soot and other wildfire indicators is consistent with a cosmic impact event at 12.9 plus or minus 0.1 thousand years ago, and the hypothesis that the Earth crossed paths with a swarm of comets or carbonaceous chondrites producing air shocks and or surface impacts that contributed to abrupt ecosystem disruption and megafaunal extinctions in North America. So that's kind of where we left off last time, was talking about these Channel Islands, right, which is off the coast of Southern California. Now, come to 2009, and we have a study in Halls Cave, Texas, which you guys were going to go visit, right?
Right.
So what do you have to report on your explorations of Halls Cave?
We put an offer in.
Okay. Okay, well, so yeah, anyways, we talked about Halls Cave, which is just in your backyards almost, right?
Yeah.
Yeah.
We were saying where we work, Kerrville.
Yeah.
But we've actually been working in Hondo, which is the other direction, for an hour and a half. So, but when we get back to Kerrville, we're going to Halls Cave.
That's right.
Okay. Because it provides a unique opportunity for testing the presence of a chronostratigraphic datum.
That's right.
Right? Another term. Everybody, I want everybody listening to memorize and remember this term, chronostratigraphic datum. Chrono, right, means time, stratigraphic. So it's a correlation between the strata layers and the succession of time intervals. So the presence of a chronostratigraphic datum, which is the younger Dryas boundary, and it containing rare and exotic proxies, including nanodiamonds, soot, and magnetic spherules, the origins of which remain controversial, but possibly derived from a cosmic impact approximately 12,900 calendar years before present. So this is the study by T.W. Stafford, E. Lundelius, James Kennett, his son, Douglas Kennett. Alan West was on this paper. Wendy Wolbach was on this paper. They describe it as being a karst collapse cave in Cretaceous limestones. And in relevance to what we were talking about earlier, the cave sequence contains an abundant small animal vertebrate fossil record, exhibiting biostratigraphic changes, and the timing of the late Pleistocene megafaunal extinction is consistent with that elsewhere in North America. So yes, you've got sediments at or within 10 centimeters of this contact contain the local extinction of 4 species of bats, the local extinction of the prairie dog, and perhaps other burrowing mammals in response, and the uppermost occurrence of 6 late Pleistocene megafaunal taxa that, although rare in the cave, do not extend younger than 12.9 thousand years ago. So here you have a mingling of small species and large species. And it would appear that the prairie dog survived, but in this particular place, as it says, it was a local extinction. So here you have a commingling of extant species, species that did survive, along with species that didn't survive. And again, notice that the species that survive are the smaller ones. Prairie dogs are smaller than mammoths, in case you were wondering. And I know, Russ, you were wondering. I saw you.
I was wondering that because
you were wondering.
Pygmy mammoths a minute ago. I was like, wait, there were little hairy elephants?
So they analyzed the sediments within this cave. And when they did, they found that there was a layer of this red clay, right? They called it a distinct lithologic layer. And they are immediately preceding the lithologic, litho means rock, right? Lithological contact containing an abundance of nanodiamonds, soot, and 2,400 parts per million of magnetic spherules and carbon spherules, all of which we interpret as evidence for a unique chronostratigraphic marker in the Western Hemisphere. Because the age of this horizon is approximately 13,000 calendar years before present, we interpret the age of the event as the beginning of the Younger Dryas cooling. So here in this cave in Texas, they found at this datum, this chronostratigraphic datum, where there was a local extinction of species, right? Also a much wider. So you had the local extinction of smaller species. You had the much wider extinction of the megafaunal species. But in this deposit, in this cave that's dating to 13,000 plus or minus, you also had these various proxies: the soot, the magnetic spherules, the carbon spherules, and the nanodiamonds. So this is, you guys have got some work to do there.
Definitely got a field trip to do.
You do.
Believe me, it will happen as soon as we get the chance to do it.
Yep.
I'm sure.
Holidays,
Well,
and all that, you know.
Hopefully, yeah. I mean, I don't know if you have any idea of what you guys are going to be able to get access to the cave.
Well, yeah, that's another question. But I think
we'll get in.
Yeah,
We'll get it.
You may have to employ your ninja skills.
Right. I'll have to dust those off.
Either that or just brute force.
Yeah.
Just blast your way in.
Yeah.
Make a new karst window. We'll get in there.
Yeah, through the karst window.
We've got some names on the papers that you know, people who were studying in there.
Yeah.
So if anything, we can contact or try to reach out to some of these people or universities or whatever and be like, hey, you know, so
yeah,
they might be down. Especially if we sing them a song.
Yeah.
Talk to the Hicks brothers.
Have you ever seen the pluvial deposits at the YDB? You know what I'm saying?
I think you got a hit on your hands there, Kyle.
That'll work.
So, a study from the Murray Springs Clovis site and the question of extraterrestrial impact. This was a paper, again, Proceedings of the National Academy of Sciences. C. Vance Haynes was the lead author, published in 2010. So they took a sample from the Murray Springs, which is where you see this really well-defined black mat layer that I think we showed a picture of a couple of episodes ago. So what they did was they studied magnetic particles found at the base of this layer and then studied them under, made microscopic examinations with 100 times amplification and 400 times magnification. So both reflected and transmitted light revealed what appear to be subangular. I mean, not quite really sharp, but more, you could think of it as more blunt angles, right? Detrital magnetite grains and rock-forming silicates with a few silvery microspherules, ranging in size from approximately 10 to 70 micrometers. They look like microscopic, highly polished ball bearings. And what I'm going to do is share a screen here so that you can see these magnification of these samples taken from the Murray Springs site. So let me do a screen share here. Here we go. Among the buried samples contains the highest percentage of magnetics separated from the microstrata. So you can see here, I've got an arrow pointing to one of these ball bearings, one of these microscopic ball bearings. Are you seeing it?
Yeah, we see it.
Great. Yes. So this is the kind of stuff that's showing up under the microscope. And this is what's showing up in abundance in the mass extinction. So, and also the same layer that's showing up the soot and the evidence of biomass burning. These things are found, these tiny microscopic ball bearings.
And are those the magnetic ones or?
Yes.
Okay, the magnetic spherules. Okay.
Mm-hmm. The Clovis occupation surface at Murray Springs is a sharp stratigraphic contact upon which rests black organic clay, which is the black mat. The Murray Springs black mat covers and preserves the Clovis age landscape. Hundreds of Clovis stone artifacts in direct association with skeletons of 2 mammoths, 11 bison, and bones of dire wolf and horse were exposed under the black mat by archaeological excavations. Interesting. So here's this black mat covering the landscape, and right under here you see these extinct species. And then when you look at the sedimentary deposits under the microscope, you start seeing these little magnetic ball bearings. We retain the opinion that we have yet to understand what happened approximately 12,900 calendar years ago that abruptly terminated the major elements of Pleistocene megafauna. The ET impact hypothesis has sparked several investigations that are leading to new knowledge, and although our data from Murray Springs and elsewhere do not support it, neither did they preclude it. So what you're having here is Vance Haynes is now, of course, this distinguished paleontologist. So him and his group are taking a very conservative view of this, right? I mean, I think he may have passed away. I mean, he's looking at this. He's probably in his late 80s in 2010 when this is being written. So he's been looking at this stuff for half a century. And he is the guy, in fact, who first identified this ubiquitous black mat layer over North America and noted the association of this black mat layer with this sharp stratigraphic shift that occurred, and that below it you had Clovis and below it you had megafauna, extinct megafauna, but not above it. So he's being very conservative here. While we're here, look up, see if you can find the term, Kyle, Rancho La Brea. Rancho La Brea.
This is Cosmographia, the Randall Carlson Podcast.